In this lesson, we will see how to analyze the complexity of recursive programs, and we will do so by picking up a very simple example of factorial of a positive integer. Now, when we talk about complexity analysis of programs, we basically mean two things. First is time complexity, which basically is the measurement of how the time taken by the program grows with the input. And another thing is space complexity, which is the measurement of how the space or the memory consumed by the program grows with input. So let's pick up a simple example of a recursive implementation of factorial of a positive integer and try to analyze it. So here in the left, I have written a recursive implementation to calculate factorial of n. If n is 0, we simply return 1, else we make a recursive call to calculate factorial of n minus 1. Multiply it with n and return the output. Now let's say time taken to calculate factorial of n is equal to tn. When we try to analyze time complexity of a program, we make an assumption that each simple operation costs us 1 unit of time. So if we see for n greater than 0, we first compare it with 0, which is one simple operation. So this has got cost of 1 unit. Then we have a multiplication operation here that we perform after we get a return from factorial of n minus 1. So this is 1 unit of cost, and we perform a subtraction here to calculate n minus 1, which is another 1 unit of cost. So tn is nothing but the time taken to calculate factorial of n minus 1, which is tn minus 1, plus 3 units of cost for these simple operations. And this is true for all n greater than 0. For n is equal to 0, t0 is equal to 1, because we only make a comparison here and simply return. Now we have tn is equal to tn minus 1 plus 3. Let's try to reduce this expression tn in terms of our known value t0. Now tn minus 1 can be written as tn minus 2 plus 3. So overall the expression will be tn minus 2 plus 6, and this can be further reduced to tn minus 3 plus 9, because tn minus 2 is nothing but tn minus 3 plus 3. So if I have to reduce this by a generic k, then this is equal to t of n minus k plus 3 into k, or 3k. Now we want to express this in terms of t0. So in that case, n minus k will be equal to 0, or k will be equal to n. So this expression would finally reduce as tn is equal to t0 plus 3n, which is nothing but 3n plus 1, because tn is 1, sorry, t0 is 1 here. So we can see here that the time taken by this particular program for an input n is directly proportional to n. And we can also say that this is big O of n in terms of time complexity, or this is an order of n algorithm. Now there are a couple of different methods to calculate time complexity of a recursive program. This is one of the methods in which we try to reduce tn in terms of its base conditions. Now let us try to analyze space complexity of this program, and I will clear this a bit, and we will again this time go by an example. Let's say we want to calculate factorial of 5, so we make a call to factorial 5, and I will write f5 here, a shortcut for factorial 5. Now f5 goes on to calculate f4 recursively. What happens at this stage is that the computer says that, hey, I will save the state of this particular function called f5, which means saving all its local variables and its current state of execution in the memory, and go ahead and calculate f4 first. And once I'm done with f4, I'll come back to f5. Let's say this is computer's memory in the right, and these partitions are some unit in which the memory is divided. So computer saves the state of f5 in the memory and goes ahead to calculate f4. Now f4 again makes a call to f3, so f4 again is saved in the memory. f3 again makes a call to f2, f2 again makes a call to f1. So all these states of the functions are getting stacked in the memory, and this goes on until we make a call to f0, and f0 does not make any further recursive call. So we can see here that in our actual implementation, even though we are not declaring any variable or assigning any memory explicitly, all these states of these functions are getting saved or stacked in the memory, and behind the scene our program is consuming all this space. We often say that an implicit stack is growing in the memory when recursion is executing. And what is the maximum size of this stack? If this structure, which is called the recursion tree, has a maximum depth of n, and maximum depth of the tree can be defined as the longest path in the tree. So if this is level 0 and this is level 1 and this is level 2, 3, 4 and 5, and each arrow here is 1 unit of length in the path, then the maximum path, the maximum depth is from L0 to L5 and it is equal to 5 units. And in this case the max depth is equal to 5. And if you draw this recursion tree for any generic n, then the max depth is equal to n. So in this particular case, the space required by the program is directly proportional to the input n. So we say that this is an order of n algorithm in terms of space complexity. So now the stack grows to a maximum of n units in this particular example. So when we are calculating f5, it grows to a maximum of 5 units, and as soon as we reach f0, then f0 simply returns 1 and it does not grow any further. And now f1 resumes, and now f1 finishes and it is also removed or popped from the stack. And now f2 resumes and f2 is also removed from the stack once it finishes. So we are kind of trying to show you a simulation of how this stack is growing and decreasing as this recursive call is finishing. Now f3 finishes and f4 resumes. Finally f4 finishes and f5 resumes, and I'll remove this stack that I've written over here. Now this f5 finally finishes and returns to its caller, maybe the main method, and finally f5 also finishes and is removed from the. Now I'll also remove this f5 from the memory here because this also finishes and returns. There are a lot of other things corresponding to this program execution, like the state of the main method and other function calls that get saved in the memory, but we only tried to show you the memory uses by this particular recursive call. So we saw that the maximum space taken by this program for an input n is n units. So the space taken is proportional to n units, proportional to n, and that's why this is an order of n algorithm in terms of space complexity. In another lesson, we will try to analyze the complexity of Fibonacci sequence. So thanks for watching.